So today I re-explain my research. This is my drawing here on the screen. The Earth would be over here, the Moon would be here, the Sun would be over here, and Mars is way over there on the left. And I have the distance to Pluto, which is this white line. So to begin, we already know the circumference and size of Earth. So to calculate the Moon next, I have some photos to show. This location right here would be where this International Space Station would be in outer space. So it's roughly 400 kilometers. So I use 400, not 460. And this here is a photo of the Moon from on Earth, and this photo is a photo of the Earth from on the Moon. So I took the size of the Moon and I calculated it proportionally to the Earth from on the Moon, and it's 3.4 Earth moons across the Earth diameter. So what I did was I needed to find where the distance from the Earth, the Moon, would be. So in order to do that, take a look at this photo. This is from the International Space Station. This here in the center here would be the Moon, and as you can see the nice blue sky here, like in the curvature on the edge of outer space. So if we go to here, the edge of space is a conventional boundary most commonly defined as Kármán line, located 100 kilometers above mean sea level. So knowing that the edge of space from, let's say, the ground to the edge of space is roughly 100 kilometers, and if we go back to this photo, the Moon is about the same size as that blue line, that curvature. So back to the drawing. We have the International Space Station, we have the ground, which is the green line, and then the edge of space, which is this blue cyan looking line. So what I did is I placed that Moon exactly where it would show up in between the Earth and the curvature that we had discussed. So then we just have this purple magenta cone-shaped line, which is referenced to the width of that Moon if it were that small inside that atmosphere. So then we grow this purple line all the way to the correct size that we calculated the Moon. So in order to do that, we would take this here, 3.4 moons across Earth diameter. So if we take the Earth diameter, which is 6378 times 2, and we divide that by 3.4, it gives us the diameter of the Moon. But we need to divide it by 2 in order to get the radius, which is 1,875. And if we check here, 1,875. So next, what I did was I calculated where the Apollo, I think 17? Yeah, Apollo 17, they filmed this video of the Earth, and they filmed in the same video the Moon, which would probably be filmed at the exact same time. Therefore, what I did is I calculated the proportion, knowing the size of the Earth and how much space is on each side of the video. This black part on the side is not part of the video, because back then we had square recordings instead of digital widescreen. So I was able to find the distance that covers from the outer edges of the Earth, and that would be our 2 of 6 pieces, 1, 2, 3, 4, 5, 6, and then 2 of those give us the 2 of 6. So what I did is I put the 2 of 6s on this side of the Earth and this side of the Earth. And I went and I did the same thing for the moon. So this would be the 7 of 7 pieces. 1, 2, 3, 4, 5, 6, 7. So knowing that and knowing the other pieces on the side of the moon, I was able to find the distance where the video was filmed during the Apollo 17 mission. So it was in fact a bit closer to the Earth than it was to the moon at the time of their video. So that explains that part. The next part would be how I found the size and distance of the sun. So to find the size and distance of the sun, we have this purple line here, which is very important because it references from the Earth to the outer edges of the moon to where the sun would be during a solar eclipse. But more so, this photo here is actually taken from on the moon, and this photo here of the sun was taken from Earth's orbit. So what I had to do in order to find the distance to the sun is, in this photo here, the sun is actually bigger than in this other photo. So what that means is this is from our Earth orbit. But if the sun is bigger from on the moon, it means that when they took the photo, the moon was actually in between the Earth and the sun, which is what made it brighter from the photograph on the moon than the photograph from Earth orbit. So that proves that the moon was closer to the sun than it was. It proves that the moon was in fact between Earth and the sun. So what I did is the Earth from on the moon, like we did earlier, but this time we're comparing it to the size of the sun. So that gives us the radius, which would be half of this, would be 6,378 kilometers, but we're calculating it in proportion to the sun. So we have 2 radiuses times 2, and then we have 16 parts if you would divide it by 8 for just one of these. But this one here is only 7 of 8 parts. So we have 2 times the radius times 2, so times 8. 8 portions. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7. So that gives us our diameter of the sun. So we divide that by 2 to get the radius of the sun. So the radius of the sun would be 18,337 kilometers. And if we check in my drawing, 18,337 kilometers. So what we had to do was, because of this important purple line of the solar eclipse, which is the moon that covers the sun, we have this purple cone, so to speak. So all I had to do was, after knowing the distance, the size of the sun, I just had to make sure that it would be properly inside these purple lines. So afterwards, because of the photographs that we have of Mars from the moon, I was able to calculate the same type of proportion. So we took the Earth diameter, which is 2 times the radius, and divided it by the number of times Mars appears at the same relativity. So we have 4.75, and that gives us a smallest possible size of the Mars diameter, which would be 2,685 kilometers. But accordingly, with the same photo, I was able to map out the circular size of the moon. So in this example, we take the moon diameter, which is actually twice the radius of the moon. So 3,751 kilometers. 3,751 kilometers. But the moon in this picture here is actually 90 times smaller than the moon. So that would give us 3,751 divided by 90 gives us 20.84 kilometers. So what I did next was, from our moon, I have our 20, oops, I'm on the wrong line. We have our 20.84 kilometers. So what we do here is we use it as a reference. So another cone, just a triangle shaped, and that gives us a projection of the size of where Mars would be. So from Mars orbit, I believe, they take this photo here, which is the photo of the Earth and the Moon, photographed from the distance Mars is at. So that gives us this one here. So we have our Earth comparison to the Moon, and we also have our Earth comparison from Mars to our Earth comparison from the Moon. And it's in fact 0.3 times smaller. So, knowing that it's 0.3 times smaller in retrospect to the Earth from the Moon, we put our triangle, our cone backwards from the Earth going to our 0.3 times smaller, and it's from the Moon, so that's why it's lined up with our Moon in the drawing. And if we follow that line all the way to where it ends up, this is where Mars shows up. So the size of Mars is actually 3,389.5 kilometers in radius. And according to the internet, it's the same number. So I somehow fell upon the correct size of Mars. But we have a different distance in my drawing from the Earth to Mars, from the Earth to the Moon, from the Moon to Mars, from Mars to the Sun, from the Sun to the Moon, and from the Sun to Earth. And all those numbers are inside of my project documentation. So this here as well is shared with my research. And if my research is somehow worth money, then, you know, pay me my money. You know, that's my research. So I hope you all enjoyed me explaining. The final part is this Venus transit in 2004, where it appears 26 times smaller, and Venus compared to the Sun is 28 times smaller in this drawing. So I just rounded it off to, instead of 26 and instead of 28, I rounded it off to 27. So if we go here, we have a shadow, which would be the 27 times smaller, represented by this circle, and the smaller one would be the same type of thing, but for Mercury, which is 140 times smaller. Now, because I don't have enough references, I can't, per se, prove exactly where Mercury and Venus would be in the drawing. But for Pluto, this photo here, I compared our Sun that's in the drawing, in the picture, to the Sun that we have from Earth orbit, and it's 17 times smaller than from the Earth. So in retrospect, 17 times smaller, what I did is I took the distance of the Sun to the Earth, because of the orbiting Sun here, from our orbit, and I multiplied that distance times 17, and that gave us the distance to Pluto. So that's my video, and I hope you enjoyed it, and I'll probably be posting it on YouTube pretty soon. So have a good rest of your day. This is my drawing.